Hello and welcome to the next episode of 3D and 30, Ahead of the Curve, exploring the benefits of CP1. Now, today we're going to be looking at an amazing alloy, and it just reminds me of times when I go to trade shows or just when I talk about metal additive in general. People tend to be amazed that we're even printing in metal. So I show them something like this, a little marketing part, and they just can't believe that that's even a technology. A lot of people have heard of plastics or composites or something like that, but metal blows their mind. And then when we think about what types of metal we're printing in, we've got nickel-based superalloys, titanium, copper, aluminum. So we'll talk about today. It's a very powerful list, and these are very high-end alloys being used to manufacture some amazing innovations. A lot of these alloys, though, have to go through a life cycle. First of all, it has to be printable at all in order to get anything out of it. And then suppliers are now pushing the envelope, and they're pushing the envelope in amazing new directions. CP1 is an alloy that fits this category, kind of fits this story. And it's been about a year. It was last May that Velo3D launched CP1. And we wanted to catch up with one of our customers who has experience using CP1 and find out what their feedback is on them. Is it as amazing as we had hoped? And so without further ado, we're going to dive into that. I do want to say, though, this is a live show. Please submit your questions. We love to hear from you. We love interacting with the audience. We've got some great speakers today. And let me go ahead and introduce our speakers. From PWR, we've got Dr. Toby Maconachie, AM engineer. And from Velo3D, we've got a technologist, and welcome to the show, both of you, first of all.
Thank you very much. Pleasure to be here.
Toby, can you give us a little bit of your background and your experience?
Sure. So I'm an additive manufacturing engineer here at PWR Advanced Cooling Technology, where we're a heat exchanger manufacturer, and I run the additive manufacturing department, so working on additive manufactured heat exchangers.
And PWR, it is primarily heat exchangers, or do you do other things as well?
So we started out as a radiator company. Then in about 2009, we were focused on motorsport always. In about 2009, we got into Formula 1, and since 2010 have been supplying the teams up until today, where we supply all of the teams on the grid. Some teams, their whole cooling system, others just some heat exchangers, because there's multiple heat exchangers in a Formula 1 car. And we also, just about any motorsport you can think of, any form of motorsport you can think of, we supply them. We started out primarily in radiators, but have expanded into all forms of heat exchangers, but also recently military and aerospace applications is a very large growing market for us as well. As electronics get smaller, the heating requirements become more dense, and we need more and more high performance and intricate designs of heat exchangers. Now we do just about any form of heat exchanger you care to name.
Awesome. And we'll get into, we talked about Monaco and some of the pre-show workup. We'll get into that a little bit. Some pretty fun stories there. What do you see as sort of stand out in the market? How does PWR stand out in the market right now? You mentioned you're in all the teams, and it sounds like a lot of progress has been made in the last dozen years or so.
Yeah, so the thing that we really excel in is bespoke heat exchangers. So that's particularly why we're attractive to race teams, is we can give you not only your conventional rectangular form factor heat exchanger, but that we can do any kind of shape you'd like. So we do profiled heat exchangers so that you can have a different shape to it, but also helically twisted heat exchangers. And particularly for racing and Formula 1, this is advantageous because you're not constrained by having to have a rectangle facing the air to get heat exchanger that radiator performance. You can contour the shape of your car, and that you see modern Formula 1, older Formula 1 is one of the striking differences is the kind of contoured shape of the cars. And we're able to produce heat exchangers that follow that contour so that you're still getting your high cooling performance without having to surrender that contoured shape.
Nice. And Suraj, kind of a little bit about your background and what do you do for Velo3D?
Sure. Hi, everyone. I got into the additive space back in grad school, actually 8 years back, where as part of my master's program at Carnegie Mellon, pursuing material science and engineering, started off my journey with additive, looking at characterizing porosity in printed components and sort of mapping them back to the key process parameters that would influence those pores. So That's where I got introduced, and then moved on to Velo and been here since then. So it's been 8 long years of multiple projects, multiple efforts. But if I were to summarize that as the technologist in the process team right now, my focus mainly revolves around two areas. The first is in developing parameter sets for new materials to basically broaden our portfolio as a company and give more options for customers to be able to print on our platform. And the second key area is just fine-tuning existing materials that are already in production, either enhance their performance further or add more capabilities. That's my role here, and that's what I've been busy with.
And you mentioned kind of the parameter sets. And so CP1 was one of the ones that you worked on, I guess, a year ago, and probably been still working on it.
Yes, so when we first that effort started off, given the nature of what this material was intended to do, a lot of focus was on switching from previously F357 to CP1. So the initial parts of the project were, I think we'll touch upon this a little bit later, but the initial parts were more of a validation to see if what we had already developed in F357 works well in CP1. And then later on, we moved on to adding more capabilities, which is finding the parameter sets for higher layer thickness, which is why we now have two options on CP1.
Nice. And Toby, I've got some photos here, some of these parts. Let me see if I can get that up there. There we go. Can you tell us a little bit about what you're holding?
Yep, so that's a charged air cooler. It cools the air that comes out of a turbo. You have the air going through kind of axially, and then you have water coming in through the side, passes through those tubes, and then goes out the other side. And so that's one of the applications. Like, there's constraints on which coolers can be made with additive manufacturing. For example, radiators need to be traditionally manufactured as per the Formula 1 rules. But a charged air cooler is one of the acceptable components that can be made out of additive, and that's one of our showpieces to more show off design and manufacturing capabilities as much as it is a high performance component. It's an example of the kind of advanced designs of coolers we're able to achieve.
And you brought a part with you as well?
Yes. So this is a housing for...
Sorry, I'm going to zoom in on you here.
So this is a housing for a microtube cooler. So you have a traditionally manufactured microtube cooler, which is one of the highest performing cooling options we have. It's hard to compete with that in terms of performance for an additive heat exchanger itself. But one of the applications we find is supporting traditional manufacturing with additive manufacturing. So this is quite a complicated piece, as you can see. It's been post-processed, it's been chemically etched, improved the surface quality. It's also been polished. That's why it's nice and shiny. And then you can see that it's got machined sections. It's an example of combining additive manufacturing with other manufacturing processes, which is where we find the greatest use for additive. And particularly the parts consolidation, that if you tried to make this by traditional manufacturing, you'd have to make all these tubes and the housing itself as individual components and then assemble them. Whereas using additive manufacturing, we can get these very complex geometries all as one part that not only simplifies the manufacturing process, but also creates just a more robust, higher performing product.
And what metal are those two components?
Sorry?
Which alloy?
Oh, yes, this has got some plastic components as part of the assembly, but yeah, it is all CP1, and you can tell it's a very kind of silvery, shiny alloy compared to, for example, F357, which is a kind of darker gray.
And the F357 was the alloy you were previously printing, and now you're printing with. What drove that change?
When we started printing with metals, which was about 2020, when we acquired a Velo Sapphire, we actually worked with you guys to develop the first aluminium process set. Until that point, you guys actually didn't offer aluminium as one of your materials. Aluminium is what we work with. It's conventional for radiators and heat exchangers. That it balances the full properties with lightweight. It's relatively cheap, and so is a really good option. It was one of the alloys available on the market. We chose that one because it was seen to be closest to 6061 T6, or it could achieve properties similar to 6061 T6. However, we had issues with it. It's effectively a 6000 series alloy, so it's silicon-magnésium, and those elements cause issues for us. So on the one hand, silicon means it's difficult to weld and gives you difficulties with heat treatment. And then the magnesium it can't be brazed. So brazing is a manufacturing technique used in radiator manufacture, where you basically assemble a radiator out of clad material. So it's aluminium tubes and fins and stuff covered with a thin layer of an aluminium alloy that melts at a lower temperature, and then you run it through the furnace and it all sticks together. But it's called controlled atmosphere brazing. The atmosphere in that furnace needs a very specific chemical composition in order to get the best braze quality, and particularly magnesium gives you issues when you try to braze with it. So CP1 comes along, it's iron aluminium alloy, and so it doesn't have the magnesium or the silicon in it. And so just immediately, based on those properties, it showed advantages for us. It also has other advantageous properties, such as very good corrosion resistance, which is also particularly important for the longevity of heat exchangers. And various other properties as well. It can be chemically treated a lot more simply than F357, and that reference we can print in thicker layers as well.
No, so a lot to unpack there. We're gonna
spend some time.
Let's take a little bit of a step back first, though. We kind of mentioned some different alloys that are available to print in, aluminum being one of them. Suraj, can you kind of give us where does all this fit? What's the landscape look like for?
In many cases, aluminum often serves as a very versatile option in several industries. And the main reason for this is because it gives you a good combination of properties. If we touch upon the ones that are quite critical. So if you look at density, it is lighter than the nickel or titanium based alloys, which makes it an ideal candidate for weight critical applications, where that weight reduction is a key driver, the types of parts that's needed. And then if you see something like thermal conductivity, well, it obviously doesn't something like copper, but the values that it's at is quite commendable. So it's quite routinely used in heat exchanger applications. And interestingly, CP1, as you have it here on this plot, shown specifically higher values than where most aluminum alloys would fall under, and in some cases even some of the other alloys. So density, thermal conductivity, and then of course there's the strength of the material. As far as the ultimate tensile strength is concerned, again, very respectable numbers. It falls somewhere between your nickel and titanium alloys. So sort of if you see all of this, it gives you all in all a good balance, which is why it makes its way into many applications.
Nice. And Clement has a question here, which I think hits right on where we're about to go. Are parts printed out of CP1 more weldable and or crack resistant than F357? And what kind of heat treatment do such parts require? So Toby, do you want to take a run at that?
Certainly. So in terms of welding, yes, CP1 we find to be more weldable than F357, particularly due to the silicon content in F357. You get a lot of porosity, whereas we haven't seen that which is one of the many advantages we see for being able to combine printed parts with traditionally manufactured components to produce the best overall heat exchanger. And then in terms of heat treatment, absolutely. So at risk of getting into the weeds here, when using F357 was quite a complicated process. You need to do stress relief of the parts on the build plate to stop them just deforming when you took them off the build plate. You then need to do a solution treatment at a high temperature at about 570 degrees Celsius, and then have a quench. And then you'd have to age for about 6 hours afterwards as well. Now, particularly that high temperature in the solution treatment and the quench caused a lot of thermal distortion. So with printed parts, you're always got variance in accuracy, even between parts on a single print. And then that's heavily compounded by thermal distortion during heat treatment when you have such high temperatures and then a quench to rapidly cool it back down again. And then if you try to machine components, it becomes very difficult, because where the machine program thinks parts are is not necessarily where they are. And so you get discrepancies between the ideal CAD and the actual printed part. Now, F357, we still do stress relief. We find that to be effective, especially for large parts, but it only needs an age. So 400 degrees for 4 hours. So it's not nearly as high a temperature. It's not as time consuming or costly, and it's simpler, but it also, we basically see very little to no thermal distortion whatsoever. So it's absolutely one of the key advantages of CP1.
So CP1 is the one that has the simpler heat treat. Is that what you're?
Yeah, absolutely. Okay. Right. Yeah. F357 needs the solution and everything, whereas CP1 only needs the age.
That makes sense. Actually, an interesting question here. I doubt it's from the famous soccer player, but Ibrahimovic asks, how would you compare CP1 to Skalmalloy?
So I actually don't have much experience with Skalmalloy. My understanding is it's a higher strength but lower ductility. That is less of for heat exchanger applications. You want that ductility where the kind of load you're seeing, so you're seeing higher temperatures and you're seeing pressure loading. The higher temperatures can bring down the mechanical properties. And then if you've got a ductile material, it might plastically deform, but it won't fail. Whereas if you've got a more brittle material, F357 was similar as well, it's more likely to crack. And I believe it's a similar thing with Skalmalloy as well.
Suraj, did you work with Skalmalloy when we qualified that?
I didn't work on it personally, but it was my team. And I think a key differentiator here is the alloy chemistry. Skalmalloy happens to be an aluminum, magnesium, scandium alloy. And again, this is what Toby was mentioning earlier. Being devoid of magnesium is one of the key aspects to the advantages that it gives in brazing applications and minimizing the likelihood of corrosion and just making your job with brazing easier. So if one of the biggest values that one's going after is being able to take these additively manufactured parts with parts that have been manufactured using other techniques, welding them, brazing them, CP1 would still be the alloy of choice.
Got it. Eric asks a question. What range of yield, tensile, and elongation results do you get for CP1? Is that something you can kind of talk about or cover?
Shall I field that one? It's comparable with F357, which is again comparable with 6061. So you're talking about a yield strength around 300 megapascals, a ultimate strength of around maybe 320, and then elongation. It's a more ductile material, so it can get up to between 10 and 20% elongation at failure. Now, of course, these factors for additive, it's not like a material just has set mechanical properties. It's dependent on the process. For example, printing with thicker layers has the advantage of higher throughput, shorter, quicker, cheaper builds. There is a little bit of a cost of mechanical properties there. And then similarly, we can apply heat treatments, surface treatments, all those kinds of things to also alter those mechanical properties. But in terms of the kind of as printed and heat treated state, yeah, you're talking similar to pretty much.
And Suraj, you mentioned 100 micron process and a 50 micron process. Like in the context of these material properties, what do you see would be the trade-off to printing faster? How would the material properties change going from one to the other?
The main trade-off would be with the tensile properties. And this is not specific to CP1. This is something that we have seen across different alloy families where you make that obvious trade-off in going to thicker layers with reduced strength. But as long as your design criterion allows for you to take that hit and still design to those numbers, you can make significant use of those savings with the throughput and cost.
Nice. Yeah, I was just kind of wondering about that when you mentioned that earlier. We do have a question from an anonymous person. Can you discuss the applications you're seeing in the emerging space markets in CP1? It's kind of an interesting.
So as far as space, it's not really an area done much work in thus far. To the degree that space interested in, it's really around the lightweight, relatively high strength, relatively low cost material. But again, particularly the sense we get is that the industry is moving away from, for additive manufactured aluminiums, particularly the silicon-magnesium alloys, because of the heat treatment. It's not only the high cost and complexity of the heat treatment, again, is that thermal distortion that's experienced during the processing of the material that causes issues for the form of the part itself. But then when you try and use it in assemblies with other components, which for race cars and for space parts as well, it always is. It's very rarely just a single printed component. It again comes back to that heat treatment that is the main advantage that we're seeing a lot of people moving away from the traditional alloys to these more advanced bespoke materials that are specifically designed for the additive process.
And Suraj, are you able to talk in maybe generic terms about some of the applications we're seeing where customers are looking, maybe not just in space, but outside of motorsport and different industries?
Yeah, so I think the key industries where it's making its way is mainly automobile and aerospace. There's been varying levels of interest in semiconductor space where I think there's a lot more of qualification process that they need to get through to convince them that it's a good enough replacement for how they currently do things. But that interest has not died out. It's always been there. It's just not made it through the finish line. But see from different areas, mainly aerospace and automobile are key adopters for CP1.
Now, the semiconductor is interesting. I used to work for Applied Materials, and we would go and service the machines in the field. And we had something called a producer, and it had two build chambers. The entire body is aluminum. It's got water transferring through it to regulate temperature, as the faceplates are aluminum. So, I could definitely see where that would make a lot of sense in an industry like that. Pretty cool. I did want to talk, so we kind of went over some of the advantages. We went over the heat treat, the corrosion resistance. We talked about the braceability due to the lack of magnesium. You mentioned the weldability. And this was something that I was wondering about this morning, because laser powder bed fusion is a welding process, like in its nature. Does that reconcile with it having challenges in weldability and then it being able to work in laser powder bed fusion in terms of like an ALSI 10MG, for example, or the F357? Were you seeing effects in the material properties during the process?
Well, that's why you heat treat it, because in its as printed form, you're heating the material up really rapidly and then it's cooling back down again. And so you're getting a really fine distribution of silicon through the part. And you need heat treatment to kind of more consolidate those silicon particles within the printed material. That's a big part of why you do the heat treatment, similar why you do a T6 on 6061. It's kind of to manage that silicon. It gives you advantages, but you also kind of have to manage the effects it has, particularly in terms of brittleness. And so when you're welding, you're kind of almost applying a local heat treatment, similarly when you're melting during the powder bed fusion process. And so in its as printed state, silicon alloys, F357, ALSI 10MG, as you said, come out in a very brittle but strong state. They have higher strength, but a failure below 5. Whereas CP1 comes out the opposite. It comes out with low properties, but very ductile. We're talking 20 to 30% elongation at failure. And it's the aging that actually brings up those mechanical properties. So yeah, I imagine that's what's going on there.
No, that's interesting. I did not put that together when we went over this earlier, but it just occurred to me. So the silicon being in the material, then even in the laser powder bed fusion process itself, because it's mainly a welding process, there are potentially residuals in there that now that's driving that heat treatment. So these all kind of end up being interconnected.
Absolutely.
That's fascinating. Well, so we're kind of getting about 2.5 minutes left. I want to make sure we have a little bit of time. These fly by. I was warning you earlier, these fly by. But Sid does mention, for those of you who are looking at AM to address aluminum casting pain points, could CP1 be a better aluminum choice than F357 or ALSI 10MG?
There's an interesting question, because ironically, F357 was developed originally as a casting alloy. It's actually been used for decades. And when additive came along and metal printing particularly, engineers, rather than design new materials for a new process, took existing materials and developed a new process. And it's taken the years of development we are into the process now for us to actually start not only developing, but bring to market, well, not us, but suppliers bring to market specifically designed for printing. So it would be completing the circle if you were to then use CP1 for casting. Don't have a lot of experience with casting myself, but hey, could well be the case.
That sounds awesome. You mentioned these material property benefits. Are there other things that you're looking for when you choose a metal or an alloy, like certifications or acceptance by different organizations? Does that play a role?
Yeah, absolutely. So Part of our adoption of CP1 was we needed to get FAI approval for it to be used in Formula One. So as part of the restrictions on Formula One is what materials can be used in which components. And so in order for a material to be accepted as acceptable, like a usable material on the grid, the team needs to make an application. So we worked with the team and Constellium, the suppliers themselves, on that application, and when it was brought to market, as you said, mid last year, it was allowed by FAI, meaning that the teams can use it for heat exchangers, which is particularly important for us.
Now I saw Monaco. I'm not a big viewer or fan, just full disclosure here, but I was amazed that like they're going from 20 miles an hour to 175 miles an hour in seconds. The technological hurdles that they must get to in order to do that and achieve that level of performance with these cars, it's unbelievable. And you're sitting right in the middle of all of this with the heat exchangers. I don't know, you probably can't say a team, but is it possible that we saw the effects of some of your heat exchangers at Monaco? Is it that they're already in the market?
Absolutely. Every team we supply heat exchangers to on the grid. Actually, there's been cases where there's been crashes and certain heat exchangers are exposed because of the damage that's done to the car. And it's like, oh, there it is, but kind of don't want the other teams to see what's there. But absolutely, yeah. The performance of current Formula One cars is in part related to the high-performing cooling products that we supply at PWR.
No, that's pretty awesome. And I was going to ask you about the crash question, but I wasn't sure if it was taboo. It's like, I don't know the third rails of Formula One yet. We're kind of up on time. I do want to have a little bit of time for closing thoughts. And Suraj, maybe can you go into some closing thoughts? And specifically, if people are interested in CP1 and they want to print components, obviously, Toby, they can go to you. But I understand Velo might have some capability for them too.
Yes. So first of all, I think we've discussed making the transition to CP1, the sort of benefits that it's offering. And from our side, all the findings and all the recipes that we had developed on F357 and that we had been using for all these years has transferred quite seamlessly over to CP1, which has eliminated the need for any extensive So we have in fact assisted a lot of our customers in making this switch, just like how PWR has made, without encountering any major red flags. Yes, so CP1 has also been successfully qualified on our large format XC system. So I'm really excited at the prospects of leveraging all of these advantages that we discussed, but with large scale components. And I was just told that there is a turbofan printed on that XC that'll be making its way to Rapid. So definitely recommend checking that out.
Yeah, this may be a picture of the smaller fan, but I believe the larger one is essentially a scaled up version of this. So imagine this fan in about a meter diameter, and about a 600 millimeter diameter. And that's what we're going to have at Rapid. It's going to be pretty impressive. And I did take a sneak peek at our downskin defect detection. It looks very clean. So that's some technology we'll be coming out with here in a little bit. So Toby, I'm going to give you the final word. What do you have for closing thoughts about this alloy, or any other thoughts?
It's a great, having made the transition, wouldn't go back. While it took a while for our customers to come around, engineers tend to be conservative when it comes to material choice. They'd rather choose something that is, generally we'll choose something that's more proven and known to be reliable than take a risk on a new material, even if it shows certain advantages. However, the advantages we've seen with CP1, particularly for heat exchangers, that the welding, the brazing, that we can combine the complex geometry that can be achieved with a printed, while still combining that with a traditionally manufactured core that we know very well how it works. It can be manufactured in a very repeatable, high-performing, robust manner, is really advantageous. And so we're seeing a whole lot of interest in particularly the advantages of the heat treatment, the corrosion resistance. All these factors that we've discussed today mean that customers are very much coming around to CP1, and I foresee that this will become a more standard alloy for additive manufacturing going forward compared to the traditional.
Perfect. And before we go, I do want to just get this question from Clement out here. Toby, do you have any tricks, printed chains, etc., to remove powder from recalcitrant passages?
Flushing a radiator is a standard part of the process, so we kind of apply some of those techniques. So we actually have highly developed rigs that basically, really all it's doing is sending water back and forth through the heat exchanger quickly with pressure. We find that to be effective, but pretty much to that point, you want to get as much out as you possibly can, because once the powder gets wet, it gets stuck in there. So yeah, it really the standard kind of things. Using vibrations, just tapping it as well, blowing it out, but also combine it with those radiator flushing techniques as well, which is not something that's necessarily available to everyone, but one of the advantages of working at a radiator manufacturer is being able to use those flushing techniques.
Yeah, and the powder is reflowable too for laser powder bed fusion, and not all AM has a reflowable powder like that, so it could be an advantage.
Yep.
Well, thank you both for your time today. The audience, amazing questions. I love the interaction. This is one of the most interactive sessions we've done. So maybe we'll do them at what are you, 6 a.m. Toby? We'll do it 6 a.m. for you more. No, but for us in the US, it's a little easier. But great job, audience. Great questions. Love this session. Love the energy of it. And with that, we are way past 30 minutes. So we're going to go ahead and close out. But again, have a great rest of your week. And thank you for joining us today.
Thanks, Mike.
Thank you.